DeepCell is a provider-side fingerprinting localization system that offers high-accuracy localization for any cell phone, regardless of its type or generation. Unlike existing client-side fingerprinting solutions, DeepCell leverages unlabeled cellular measurements recorded by the cellular provider, opportunistically synchronizing with selected client devices to obtain location labels. This approach enables ubiquitous deployment and accuracy, overcoming the limitations of traditional GPS, Wi-Fi, and sensor-based localization systems. DeepCell addresses several challenges, including handling unlabeled data from the provider side, noise and sparsity in the data, scaling to large areas, and providing sufficient data for training deep models without overhead. To achieve this, DeepCell uses a novel approach to build the fingerprint from the provider's unlabeled data, automatically capturing the unique signatures of different cell towers at different locations. The system architecture consists of two phases: offline training and online tracking. During the offline phase, the provider's cellular data is used to build a fingerprint, which is then used to train a deep neural network model. This model is harnessed for localization during the online phase. The provider's cellular data contains records of phone events, including cell tower changes, with each record consisting of event type, timestamp, phone ID, active cell towers, and neighboring cell towers information. Evaluation of DeepCell in a realistic environment shows that it can achieve a consistent median accuracy of 29 meters, outperforming state-of-the-art client-based cellular localization systems by more than 75.4%. This accuracy is extended to low-end phones, demonstrating the system's ubiquitous nature. DeepCell's zero extra energy consumption compared to normal phone operation makes it an attractive solution for accurate and energy-efficient localization. The paper is organized into sections, including provider cellular data, system architecture, DeepCell system details, evaluation, related work, and conclusion. The proposed system has significant implications for various mobile applications that require outdoor position information, such as navigation systems, location-based advertisements, and emergency services. The DeepCell system is designed for ubiquitous accurate provider-side cellular-based localization. It consists of several modules including the offline spatial augmenter, grid generator, model trainer, data collector, and online data synchronizer. The system collects GPS traces from war drivers and cellular measurements from the provider's database. The GPS traces are synchronized with the provider's cellular data, and the spatial augmenter handles noise and sparsity in the provider's data by predicting unknown cellular measurements for new locations. The grid generator divides the area of interest into a virtual grid, and each training sample is mapped to a specific cell. The model trainer trains a deep neural network using the spatially augmented fingerprint samples. The system's architecture and modules are designed to overcome challenges such as building the fingerprint without overhead, handling noise and sparsity, scaling data to large areas, and providing enough training data. The system's performance is evaluated in terms of accuracy and computational complexity. DeepCell is a novel approach to cellular-based localization that leverages deep learning to provide accurate location estimates. The system consists of several modules, including a data collector, spatial augmenter, and grid estimator. The data collector gathers cellular measurements from various cell towers in the environment, while the spatial augmenter generates additional data points to enhance the model's robustness. The grid estimator module uses a trained deep neural network to predict the user's location based on the input cellular measurements. The deep network model employed by DeepCell is a multinomial logistic model, which acts as a nonlinear function to infer the probability distribution of different grid cells. The model learns the relationship between the input features, cellular measurements, and the grid cell's probability distribution through training. To mitigate the effect of noise in the input training samples and increase model robustness, DeepCell uses a dropout regularization technique during training. During the online user tracking phase, DeepCell depends only on the phone ID as an input. The grid estimator module estimates the discrete grid cell in which the user exists given the cellular measurements vector. The center of mass of the estimated grid cell represents a coarse-grained location estimate of the user location. To further refine the estimated position in the continuous space, The Fine Estimator module estimates the user location as the center of mass of all grid cells, weighted by their respective probability. DeepCell's performance was evaluated in a test bed covering a 2.04 square kilometers area in a typical urban area in Alexandria, Egypt. The system demonstrated accurate location estimates, outperforming state-of-the-art techniques. The effect of different parameters on DeepCell's performance was also studied, including the effect of fingerprint models, grid spacing, number of augmented samples, cell towers density, number of training epochs, and learning rate. The results showed that the best structure for the deep network model contains 3 hidden layers with 256, 128, and 64 neurons, producing a consistent accuracy. The research paper discusses DeepCell, a ubiquitous accurate provider-side cellular-based localization system. It leverages cellular RSS measurements from different cell towers to train a deep neural network model for outdoor localization. The system's accuracy is enhanced by incorporating active cells information, spatial augmentation, and cell towers density. Figures and tables demonstrate the impact of various parameters such as fingerprint models, grid cell length, number of augmented samples, cell towers density, training epochs, and learning rate on the system's accuracy. Comparisons with state-of-the-art systems like DeepLock show that DeepCell achieves better localization accuracy by more than 75.4%. The paper also discusses related work, highlighting the limitations of GPS-based and sensors-based techniques and the advantages of DeepCell's energy-efficient and ubiquitous coverage. DeepCell is a provider-side cellular-based localization system that leverages ubiquitous cellular network coverage to provide high-accuracy localization for any cell phone. It builds a radio map from provider cellular unlabeled data and uses a deep neural network model for localization. The system's design includes provisions to handle system challenges and noise in the input data. It outperforms state-of-the-art cellular-based localization systems by more than 75.4% with a median accuracy of 29 meters. Here is the combined summary of pages 11 and 12. DeepCell is a ubiquitous and accurate provider-side cellular-based localization system that leverages machine learning and signal processing techniques to provide accurate location information. The system builds upon previous works in Wi-Fi-based localization, such as dynamic SLAM, which utilizes human anchors for low-overhead indoor localization. DeepCell also draws inspiration from outdoor cellular localization systems like DeepLock, which achieves high accuracy with low overhead. The system employs a neural network architecture with dropout regularization to prevent overfitting, as introduced by Shrivastava et al. The neural network is trained on a dataset of cellular signals and corresponding locations, allowing it to learn the complex relationships between signal patterns and geographic locations. DeepCell's approach differs from traditional fingerprint-based outdoor localization methods, which rely on extensive wardriving to create a database of signal fingerprints. Instead, DeepCell uses a crowdsourced approach, leveraging mobile devices to collect signal data and provide location information. This approach is more energy efficient and scalable than traditional methods. The system's accuracy is evaluated using a dataset of cellular signals and corresponding locations, with results showing high accuracy in both urban and rural areas. The evaluation also compares DeepCell's performance to other state-of-the-art localization systems, including VTrack and Horus WLAN. DeepCell's advantages include its ubiquity, accuracy, and low overhead, making it a suitable solution for various applications, such as location-based services, traffic monitoring, and emergency response systems. However, the system assumes the availability of cellular signals, which may not be present in all areas, and relies on the quality of the crowdsourced data. Future work includes exploring the use of other sensor modalities, such as GPS and accelerometer data, to further improve the system's accuracy and robustness.